All right, so we're looking at page 26, Pascal's triangle, binomial expansion. If you already were in class and saw all this stuff, you can just hop ahead to page 30. For some classes it was a separate handout, so make sure you have a copy of that. But it might be a recap for some people, but just to kind of take you through this. The do now here, fill in the table. So we have x plus 1 to the 0th power. Anything to the 0th power is 1. X plus 1 to the first power, x plus 1. The coefficients, I can do this as we go. X squared plus 2x plus 1. Coefficients 1, 2, 1. And then x to the third plus 3x squared plus 3x plus 1. Coefficients 1, 3, 3, 1. So this serves as sort of a reminder of how the Pascal's triangle sort of came into being. Right? So if you recognize that each row begins and ends with a 1, and every entry in the row, aside from that, would be the sum of two consecutive values in the previous row. So 1 plus 2 gives me a 3, 2 plus 1 gives me a 3. And if I needed the next row, I'd get a 4, again, starting and ending with a 1. 6, 4, and 1. All right. I gave this this mega table here, or mega triangle, but the idea is really the same. So this first and last entries are going to be the same across the board, all equal to 1. Consecutive values all add to give me the next, or the entry in the next row. So 5, 10, 10, 5, 1. So start and end with a 1. 6, 15, 20, 15, 6, and 1. And, I'll just do one more. All right. Hopefully nobody will ever accuse me of giving busy work. But if I were to ask you to complete this entire triangle, I think that would fall into the category of busy work. All right. You get the idea at this point. You also get the idea that if I needed to raise x plus 1 to the 15th power using Pascal's triangle, I'd have to complete a very, very large triangle in order to get those coefficients. So if you have it in your mind that there has to be an easier way, we'll call it easier, but we'll say a different way, then that's a good thought, right? Because we'll get there, but for now, we'll continue with Pascal's triangle. I typed up an example, a guided example. We'll do the now you try something different here. I put the answer at the bottom, but I'll carry you through it. All right. So here you'll see it's not as simple as just an x plus 1 raised to the 4th power, but we still use Pascal's triangle. All right. I need to get out to the 5th row. Whatever the second entry is in the row corresponds, as it turns out, with the power. All right. So we used x plus 1 before, but the rule here is that aside from listing out the coefficients, the exponents still follow the same pattern, except we're taking the entire term, and that'll be the x term of the expansion. Typically what you would see is something like a plus b to the, I'll just say to the 4th power, would be equal to a to the 4th plus, I would use my coefficients of 4, a to the 3rd b, plus 6, a to the 2nd, b to the 2nd, plus 4, a, b to the 3rd, plus b to the 4th. right? And if I had to do that to like a plus b to the 15th power, you can imagine that that's going to be fairly lengthy. But really, it's each term in the given binomial that's going to take on the role of a and b. So you could think of it as just kind of a massive substitution, but it still follows the same structure. Right? So I would list my coefficients 1, 4, 6, 4, and 1. Right? Instead of saying a to the 4th, I would say 3x to the 4th. And then there is no b factor in that first term, but that's because b is raised to the 0th power, which becomes a 1. If you wanted to put it in, you could, but most people don't. Right? So then I would have my 3x to the 3rd. My negative 1 would go to the 1st power. 3x to the 2nd, my negative 1 would go to the 2nd. 3x to the 1st, my negative 1 would go to the 3rd. And then 3x would go to the 0th, which disappears. So I'd have negative 1 to the 4th. All right. So just like we'd been doing with Pascal's triangle, all that's happening here is we list out our coefficients. We take our first term, raise it to whatever that high power is, in this case, power of 4, and then decrease that high power as you go from left to right. Right. So getting one smaller every step of the way until it disappears. Right. Whereas, so I'll get rid of that. The 4 becomes a 3, becomes a 2, becomes a 1, and then disappears. All right. Throw some plus signs in there. Any negative values will work themselves out through the calculation. 3 to the 4th power is 81, so 81x to the 4th. 3 to the 3rd power is 27 times 4. 27 times 4 is the same as 27 times 2 times 2, so 108. X to the 3rd, but actually looking at it, almost, oops, a little too big on that eraser there. I do have a negative 1 multiplier here. So yeah, it's going to be 108, but it'll be negative. So negative 108 x to the 3rd. Anything that's raised to, any negative that's raised to an even power is going to become positive. So I could disregard this one and this one. 3x squared is 9x to the 2nd power. 9 times 6 is 54, so plus 54x to the 2nd. Minus, we have alternating signs. It goes from positive to negative, back to negative, and so on, until you run out of room. So 4 times 3 is 12x, and then plus a 1, all right, which corresponds with what I had down here, which tends to mean that it's right. Although since I'm the one who came up with this answer, you never truly know, but pretty confident. You could always check in your calculator too. Graph the original, graph the expansion, and see if they map to the same location. So we're going to hop over page 28. That's a worksheet where you can practice some Pascal's triangle stuff. We'll go on to binomial theorem for polynomial expansion. All right, so you can see a really lovely set of formulas here. And I'll talk you through what's really happening here. But I'll just give you very quickly the rationale behind it. And I mentioned before in the, we're on page, so it would be page 26, I think. I can just go back and look. Yeah, this triangle here, if I needed to raise something, a plus b to the 15th power, I'd have to create like a ginormous triangle. So instead of doing that, we could use the binomial expansion approach using combinations, all right, and summations to help us figure that out. This way we could jump right to the coefficients without having to do all the triangle work. All right. Now, if it's something that's raised to like the 5th power, 7th power even, you can even make a case going out to the 10th power. You might consider Pascal's triangle as the best approach. But anything larger than that, now it's kind of like, I think it might be in the territory of more trouble than it's worth. So we would use another technique. But let me talk to you about the structure here. So you have the summation. That's this right here. That's telling us to add up all of these terms going from a k value of 0 to a k value of n. All right, and I'll show you what that looks like in a minute. So n is going to correspond to whatever the power was of the binomial. So that top number there, here, that's all related to the power of the binomial. We're starting off with k equals 0, right? So that's we can call it the 0th term of the polynomial, right? But if I have a second degree polynomial, like a quadratic, there's 3 terms, right? So there's the 0th, the first, and the second term, right? Total of 3 terms, but starting off with a power of 0, or ending with a power of 0 in that case, right? So we will always have one more term than the highest power, so starting off with 0 allows for that, right? Well, among other reasons, right? The k value is how we increment. So we would go for the 0th term, so we plug in a 0 for k, right? So the 0 goes in for k, then a 1, then a 2, then a 3, then a 4, all the way up to whatever the n value is, right? That's how we come up with each term of the expansion, right? Or at least one way. This looks kind of weird, so I'm going to do it like this. Just kind of clean it up. 1, 2, 3, and then all the way to the nth. And I'll just grab this here. Throw in some commas. So k is going to go from 0 to 1 to 2 to 3 all the way up to the nth term of the polynomial, all going in for k. And since k is represented in a few different places, we would account for that. The other thing to keep in mind is that we don't actually need to rely too much on this formula, just the overall structure of it. And the reason behind that is if we know that the exponents are going to decrease from left to right, so starting off with your highest exponent, I could write it like this if I want to, but this is essentially saying that power of 4 becomes power of 3, becomes power of 2, becomes power of 1, and so on. We kind of have everything we need once we come up with our coefficients, because the rest is just simple algebra, right? Simple, not always easy, right? If you wanted to know where that n over k in the parentheses came from, that's a combination, and this is the formula for that. That being said, we can do it in our calculator. I made a little note here in this little table on the side. In NumWorks Toolbox Probability Combinatorics. So Toolbox Probability Combinatorics, that first entry there. So if I needed 5 over a 2, like you see in this example here, I can get it straight away. Part of that combination formula is a factorial, right? That's also in the same menu. So if I needed something like 5 factorial, I could just go to the toolbox and get that result, right? So that would be 120. That might fall in the category of like nice to know, but not really necessary, because if I'm letting you use a calculator, those formulas wouldn't necessarily be relevant. But it is kind of a nice thing to have an idea of what's happening behind the scenes, even if you don't have to use it every single time. All right, so for number 1, using the binomial theorem, I would expand this polynomial. All right, so p of x, I'm going to make a little note here, p of x is equal to 2x plus 1 to the 5th. All right, just like Pascal's triangle, I'm going to identify my a and my b values. So this is my a, and this is my b. And I also have my n. While I'm highlighting things, I'll do that. All right, so this is going to be equal to the sum from k equals 0 to 5. My combination 5k, my a value which is a 2x raised to the 5 minus k power. All right, so 5 minus k corresponds to that first exponent. So if I put in a 0 for k, I get a result of 5, and our a term, if I'm using Pascal's triangle, would start off being raised to the high power, which is consistent. All right, then I would have my negative, geez, it's right in front of me, positive 1. So 1 to the just the k power. All right, so if I want to, because 1 to any power is going to be equal to 1, so no change there. This is really just going to boil down to what I know about that first term there and my combination. All right, so in my expansion, I'll do the whole thing out though. I would have, we start off with a k value of 0, so 5 combination 0, 2x to the 5 minus 0, 1 to the 0th. Then I would decrease a 5. Sorry, I'm going to decrease my exponent overall, but I'm increasing my k. 2x raised to the 5 minus 1, 1 to the first. Then increase my k. You see how the 5 minus 0, which is 5, this guy right here, becomes 5 minus 1, which is 4, so I'm decreasing my exponent by 1 every step of the way. All right. And you can start skipping a couple steps here and there if that works for you. 5, 2, 2x to the 5 minus 2, 1 to the second, 5, oops, resist the urge to make it a fraction, 2x to the 5 minus 3, 1 to the third, 5, 4, 2x to the 5 minus 4, 1 to the fourth, and then the last term plus 5, 5. Get into my calculator here. 2x to the 5 minus 5, and then 1 to the 5th power. All right, so to tackle my combinations here, I'll just put a little equal sign here. 5, so I'll go to my toolbox, probability, combinatorics, select that first option, 5, 0. You'll notice over time that any combination where 0 is on the bottom, the result is equal to a 1. So that kind of makes things a little bit more streamlined. Any combination where 1 is on the bottom is whatever the top number is. So 5 combination 1 would be equal to 5. And any instance where the top and bottom numbers are the same, the result is always equal to 1. So if you can kind of latch onto those things, that'll be helpful. Right, so here the only relevant part would be the 2x to the 5th power. 2 to the 5th is 32, so 32x to the 5th. All right, then I would have 5, again 5 with a 1, the result is going to be 5. All right, the other relevant part here, so we care about this and we care about this. 5 minus 1 is 4, 2 to the 4th power is 16 times the 5 is going to be 80. So plus 80 x to the 4th. Combination 5, 2, that's going to be equal to 10. All right. 2x to the 3rd power, raise the whole thing to the 3rd power is 8x cubed times 10, so plus 80x to the 3rd. Plus 5 combination 3 is also 10. 2x to the 2nd power is going to be 4x squared. 4x squared times 10 is 40x squared. Same idea, 5, 4 is a 5. 2x to the first power is just 2x, so 10x. And this goes to a 1, this goes to a 1. So does this. 1 times 1 times 1 is 1. And this, I believe, is the same problem from one of those Pascal triangle questions. So, so you should be able to verify that. But you could also chuck it into the calculator. Let's see here. I had a similar problem that I did earlier. I think I have some of this stuff in. Actually, I have the right binomial, but I made it alternating for that one. Okay, I'll just change my signs here. But it should be the same thing, roughly, or close. And just a quick check. When you graph them, if they end up giving you the same function, then you know you did it right. And so that would be my p of x. All right, so p of x is equal to that expansion. Now, if you're looking for a shortcut, really, if you think about how this compares to Pascal's triangle, the only difference is we now have the ability to come up with the coefficients without having to draw out the entire triangle. So I'll show you for the second one. If you wanted to come up with the coefficients, one way to do it, I mean, it is to the 8th power. You could go into your home screen calculation app, probability combinatorics, start off with a 0, get a result. That would be my first coefficient. Now, if it is Pascal's triangle, we know that it's going to begin and end with a 1, so why would this be any different? This is really just another way of looking at Pascal's triangle. So I'd have my first coefficient would be a 1, my last coefficient would be a 1. All right. So then it would be, again, identify my A and B values. Now, B in this case is a little bit crunchier, but it's still manageable. So 1 to the 8th power, negative 2x to the negative 3rd to the 0th power, plus combination 8, 1, so 8, 1 to the 7th. And again, recognize the little shortcuts when they emerge. 1 to any power is going to disappear anyway. So it begs the question, do I even need to write it to begin with? Right? I'll leave that up to you. But I would have negative 2x to the negative 3rd would now be raised to the 1st power, plus 8 with a 2. So 28, 1 to the 6th, negative 2x to the negative 3rd to the 2nd, plus, do it again, 56, 1 to the 5th, negative 2x to the negative 3rd to the 3rd. As long as your exponents add to 8, you can be reasonably sure that you're not messing the whole thing up, but, you know, just be careful anyway. 70, 1 to the 4th, negative 2x to the negative 3rd is going to go up to the 4th. There is symmetry in Pascal's triangle's coefficients. So once you kind of hit the maximum, you turn around and the coefficients the rest of the way are going to be the same, but in reverse. Right? So 56, 1 to the 3rd, negative 2x to the negative 3rd raised to the 5th. I got 3 more terms coming up, so I can continue it off over here. So plus 28. I left off at exponents of 3 and 5. So 1 to the 2nd, then to the 6th, plus 8, 1 to the 1st, then to the 7th, and then back to a 1, 1 to the 0th, negative 2x to the negative 3rd, raised to the 8th. there's not much I can do in terms of simplifying here. I mean, unless I wanted to work or manipulate the negative exponents, doable, but you know, where are we going with this problem? It's not like a part of an application question or anything, so you know, it's kind of to learn the skills, so we don't really need to go too crazy with that. That first term ends up being a 1. Then I would have minus 16 x to the negative third. Looking at this one over here. So again, any of these 1 to the powers, you just wipe them all out. They're irrelevant. All right, I'll just cross them all off. Just get them out of my sight. All right, and so for this one here, I'm raising the negative 2 to the second power, which is going to be a 4 times 28. All right, so 28 times 4 is 28 times 2. 56 times 2 again, which is 112. So plus 112 x to the negative third. Okay, so cleaning it up a little bit, might get a calculator involved. If I raise negative 2, sorry, that's negative 6 power, because we also have to multiply the exponents. All right, so we'll highlight that. So these get multiplied also. All right, so we raise the negative 2 to the second, but then also the x to the negative third needs to be raised to the negative second, which becomes x to the negative sixth. All right. Then negative 2 to the third is going to be negative 8. So 8 times 56, so negative 448. X to the negative ninth. All right. So you notice that we're looking at multiples of 3, or multiples of 3. We're subtracting 3 from our exponent every step of the way. So you could make use of that shortcut a little bit. So that's this one we just took care of. So negative 2 to the fourth is going to be 16 times 70. So 1,120 x to the negative 12th. Then for this one, I have negative 2 to the fifth, which is negative 32 times 56. And that's going to be x to the negative 15th. So minus 1792 x to the negative 15th. Now this ends up not being polynomial anymore because we have negative exponents, but it was defined as p to the f of x. I was going to say p of x, but it actually wasn't. It was f of x to begin with. So it's almost like I accounted for that when I designed the problem, and then immediately forgot that I accounted for that. All right, so we're up to this one here. So negative 2 to the 6th power. That's going to be 64. I'll type it in anyway, though. All right. Positive, because it's an even power, times 28, 1792. So let me tuck that in there, plus 1792x to the negative 18th. All right, so coincidentally, right? But really, if you think about it, 28 is half of 56, and we're multiplying by an extra 2, so it kind of works out, or at least you should be able to sort of make your peace with that. All right, 2 to the 7th is going to be 128 times 8, 1024, but negative x to the negative 21st power, and then plus 2 to the 8th power is 256, which does not start with a 5. X to the negative 24th. Okay, so 2 again to the 8th, 256, x to the negative 4th. And we could check this. all right, just like before. You get to a point where you no longer want to check it because of the length of it, but to the 8th power it's bad, but it's not terrible. Well, it might be terrible, but it's not like can't do it, there's no point. It's just maybe you're not looking forward to doing it. All right. But here we are. So 1 minus 16x raised to the negative third plus 112 x raised to the negative sixth minus 448 x raised to the negative ninth plus 1120 x raised to the negative 15th lost my place here, negative 12, sorry. Oh no, start over. 1 minus 16x raised to the negative third plus 112 x raised to the negative sixth minus 448 x raised to the negative ninth plus 1120 x raised to the negative 12th minus 1792 x raised to the negative 15th plus 1792 x raised to the negative 18th minus 1024 x raised to the negative 21st plus 256 x raised to the negative 24th. Oof. All right. After all that, if it ended up not being right, I would not have been thrilled, but it looks like, regardless of what the graph looks like, it's occupying the same location, so we're in good shape there. If you want to zoom out and have a different look at it, that's okay too. But pretty comfortable that that we just did that the right way. All right. Number 3 is find the third term of the expansion of the polynomial. All right. So here, I don't need to list out the entire thing in order to come up with this result, and that's where this binomial theorem comes into play. All right. So just going back to an example that we already did, if I had, let's say, this term here, this is my second term, the second term of my expansion, right? Second term. That second term corresponds with a k value of 1. All right, so the term position is always 1 more than whatever the k value is. All right, so I'm looking for k equal to 2 here. So if I want the third term of this expansion, I don't need to do the entire summation, right? Just the part of it that's relevant, right? So still have to identify our A, our B, and our N, but my third term, term is going to be 6 with a k value of 2, x to the 6 minus 2, 1 to the second power. All right. So in my calculation app, toolbox, probability combinatorics, get my combination, 6 with a 2, x to the 4th times 1. So I really only care about the 6 combination 2. So 15x to the 4th would be the relevant value. If I need to do it to the 99th power and find the 78th term, all right, so here k is equal to 77, all right, 1 less than whatever the term position is. My 78th term 99 over 77. Now, I'll show you very quickly. If I put in 99 over 77, I get this monstrous number that I would never expect you to write and never want to write myself. So I would actually leave my answer in this form. So x raised to the 99 minus 78 times 1 to the 78th power. I'll just put that. I'm sorry, 77th power. Looking at the wrong thing. So my final answer here would have the combination in it. And that would be x to the 22nd. All right. 99 combination 77, x to the 22nd would be the final. 13th term, all right, a little bit more elaborate, but k is going to be equal to 12. 13th term of this polynomial, which is going up to the 21st power, so term 2112, 3x to the 21 minus 12, and then negative 7 raised to the 12th power. All right, again, numbers pretty hideous. I'll put in the 2112. I get that number. Now 7 to the 12th power, it's already crazy. All right, so the only thing that I would do here is kind of clean it up a little bit and write this as 21 over 12. 21 minus 12 is 9. 3 to the 9th power is not terribly crazy, but the way I would write it would be to say, instead of writing that number, I would say 3 to the 9th, x to the 9th times 7. I would drop the negative because it's going to an even power, 7 to the 12th. And that is what I would leave as my final answer. Then number 6, we're saying f of x can be approximated by this polynomial, right? Lovely looking polynomial. If I want to approximate e to the x using that function, then one thing that I could do, I would expand it out. All right, we'll start off with that, going from 0 to 6. So 1 over 0 factorial, x to the 0th, plus 1 over 1 factorial, x to the 1st, plus 1 over 2 factorial, x to the 2nd, all the way to the x to the 6th. And the one last one, 1 over 6 factorial, x to the 6th. All right. Now, same menu, just factorial. If I put in a 0 factorial, you would think it would be equal to 0, but through some probability concepts, which I'll explain down the line, gives a result of 1. So my first term here for p of x is equal to 1. So 1 plus x plus, because 1 factorial is equal to 1, 2 factorial is equal to 2, so plus 1/2 x squared. 1 over 3 factorial, I'll just do the 3 factorial. So 1 over 6 x to the 3rd. 1 over 24 x to the 4th. This ends up being 1 over 120 x to the 5th plus 1 over 720 x to the 6th. All right. Now, this is asking me if I know that I'm defining, oh, sorry, did it again, f of x. Yeah, I was probably better off to just change it in the other place. So I'll call this p of x. All right, typos abound. All right, but if I tell you p of x is e to the x, and I'm looking at e to the second, then I must be trying to find p of 2, right? So there's a couple of ways that you can handle this. One, if you wanted to use the remainder theorem, you could, but really all this is telling you to do is figure out what p of 2 is equal to. So 1 plus 2 plus 1/2 times 2 squared plus 1 over 6 times 2 to the third, 1 over 24 times 2 to the fourth, 1 over 120 times 2 to the fifth, plus 1 over 720, I lost my power of 6 here, times 2 to the sixth, and then just simplify. All right, so 1 plus 2 plus another 2 plus 8 over 6, all right, so 4/3, plus 16 over 24 is 2/3, plus 32 over 120, 4/15, plus 2 to the sixth is 64, divided by 720 is 4/45. So I would just add all these numbers up. 1 plus 2 plus 2 plus 4/3 plus 2/3 plus 4/15 plus 4 over 45. And we end up with about, well, it's 331 over 45, which is about 7.4-ish. Right, so e to the second, if you just type that in, gives you something in that neighborhood, 7.4-ish. Right, so this gives us an approximation for e using summations, our knowledge of polynomials and things like that. Right, if I included more terms of this expansion, I would get closer and closer to that precise value of e to the second power. Right, so you should be able to handle any kind of problem I can throw at you now. I know this is a long one, but hopefully you found this to be helpful.